Coulomb's law elegantly calculates electric fields for isolated point charges. In a vacuum, their interaction is direct. Even with more charges, the superposition principle keeps it manageable. Individual fields are calculated and added together to find the total resultant vector. This works perfectly in a textbook environment, but the physical objects we interact with, like a plastic comb or a metal sphere, present a different level of complexity. While the laws of physics don't change, the sheer quantity of charges in a macroscopic object makes the simple math of individual point charges computationally impractical. A tiny charge of just 1 microcoulomb, roughly what you'd get from rubbing a balloon on your hair, contains approximately 10 trillion individual electrons. If we look inside a charged sphere, we find a chaotic swarm of 10 trillion particles, each generating its own electric field simultaneously. Attempting to perform vector addition for easily one of those points would exceed the processing power of any modern supercomputer. At this scale, the grainy nature of electricity becomes a problem. These discrete electrons are separated by gaps where there is no charge, which prevents us from using standard geometric equations. To solve for the fields of real-world objects, physicists stop looking at individual particles and adopt a macroscopic framework that averages these effects. We resolve this by changing our perspective. When we zoom out, those trillions of individual particles visually and mathematically blur into a solid, unbroken distribution. It's the same logic used in fluid dynamics. An engineer focuses on the continuous flow of a river, rather than tracking every individual H2O molecule. We call this a continuous charge distribution. By treating charge as a smooth property spread across an object, we can apply more sophisticated math to massive structures. By utilizing this macroscopic approximation, we trade the impossible complexity of trillions of particles for the clarity of a single continuous function. Our ability to use this math depends entirely on how the physical shape of an object spreads the charge. For one-dimensional objects like a thin wire, we define the linear charge density, represented by the Greek letter lambda. Lambda is simply the charge per unit length. Whether the wire stretches or shrinks, as long as the distribution is uniform, that ratio remains constant. For two-dimensional objects like a flat sheet, we use surface charge density, or sigma. Sigma allows us to calculate how charge is distributed across a specific area element on a surface. Finally, for 3D objects, we define the volume charge density, known as ρ. ρ measures how much charge is packed inside a specific three-dimensional volume element. These three densities, lambda, sigma, and ρ, serve as translation tools, converting physical shapes into pure math without needing to account for individual electrons. How do we use these densities to find the actual electric field at a point in space? We start by isolating one tiny element of a massive object. Macroscopically, it's incredibly small, yet contains many microscopic charges. Because it's so small, we treat it as a point charge, drawing a single electric field vector toward our target point P. We use Coulomb's law on this isolated segment to find its fractional contribution. By repeating this for every segment and summing the resulting vectors, they merge into one final accurate electric field for the entire object. We've moved from the messy reality of trillions of particles to the smooth, predictable mathematics of continuous distributions. This summation technique is a powerful tool, but physics provides an even more efficient shortcut for objects with high degrees of symmetry. Mastering these geometric densities, lambda, sigma, and ρ, is the essential step that leads into Gauss's law, our primary tool for solving real-world electromagnetic problems.